Okay, we're going to get started now and pass it off to Victor and Reyes.
Hi, thanks for the intro, Emily. So this is Victor Lee, and with me is my partner, Reyes Pasha, and we're here today to talk to you about why TigerGraph is much faster than the competition from an architectural standpoint, and give you some insight into the architecture. I'm the head of product strategy and developer relations at TigerGraph, and Reyes works with me as a principal product manager focusing on the database core. We just have a few reminders for you about the webinar. We're using Zoom. All your audio is muted, but you can ask questions using the Q&A tab in your Zoom menu. There's a chat menu and a Q&A tab, and we prefer that you use questions regarding the content that you would like we, the presenters, to answer in the Q&A tab. If you want to share something with everybody that you need to for some reason, you could use, that's what the chat would be good for, or if you're having a technical issue. So the webinar is being recorded. So you'll get a link to the webinar recording, and we're also going to send you a copy of the slides. So again, if you are having any Zoom issues, contact us through chat. You can see both the Q&A chat buttons at the bottom. And with that, I'm going to let Reyes get right started into the material because we've got a lot to say today.
Thank you, Victor, for the introductions. Hello, everyone. First, I want to thank all the attendees for your interest in learning about TigerGraph architecture and how TigerGraph can help you with your graph analytics solution development. I'd like to start the webinar with an outline of today's presentation. First, we'd like to start with the system architecture overview to give you an understanding of the overall TigerGraph design and the key features. Next, we'll dig deeper into the key aspects of how the data interacts with the system. So we've tried to structure the presentation in a way where how the data gets ingested and stored inside the TigerGraph system and how the data is processed, and then eventually how the data is retrieved by the user. And then finally, we're gonna present details on the non-functional features, which are very critical for enterprises, for enterprise adoption. And these are the things that are things like high availability, transaction management, security. We'll give you a more in-depth design of these key features. As Victor mentioned, we'll answer all your questions. If you have any at the end, if time permitting, and also on the chat window, please log your questions. So starting off with the system architecture, if you look at, as the title suggests, we maybe a bit provocatively that we take TigerGraph performance, we take great pride in its performance. And if you review our performance benchmarking data for a lot of the industry standard workloads, TigerGraph is clearly ahead of the competition. And in fact, in some parts of those industry workloads don't even complete on other systems. And there's a reason for that. There's a reason because a lot of the systems are not designed to scale to the level of data volumes and concurrency that's expected. Now, the secret sauce, so to speak, behind this is not just one feature or one thing. It's the overall architecture, the entire architecture, which is a fresh implementation built ground up, and as a brand new system that was developed, and all the elements required to support that sort of scale were incorporated from the get-go, from the very beginning, natively. So basically, I want to start there with the first architecture overview to see where does our the power comes from. So let's start with some key features, like more than a feature is the feature areas. The three areas that I want to emphasize are real-time deep link querying, how we handle massive data, and how we enable in-database analytics. Let's start one by one. First, if you look at real-time deep link querying, what does it mean? It means ability to perform analysis on deeply connected data. Because if you think about the use cases that you have with Graph, these are typically, we're dealing with really connected data, where analysis can lead to connected data multiple hops, from 5 to 10 hops. And that's pretty much the key reason why folks use graph database, because when they want to get the hidden connections patterns in the data, they need a system that can easily traverse data into 5 or 10 hops without performance issues. And that's what we deliver with this real-time deep link querying. And the reason it's possible is because of our native graph design. We are not a bolt-on engine where the graph, the storage implementation is different from the engine implementation. Like I said, everything is built from the ground up. So that basically that allows us to uncover hidden patterns without, without engine running into issues with scale or performance. And the second thing that's even critical is the implementation itself. It's not just the design. The engine was implemented in C++ for performance reasons. This is what enables us to provide answers in real time, because some systems may be able to do deep link querying and uncover data, but the response time may not be something that's useful from a business perspective, because a lot of the use cases like fraud and all require us to, and even healthcare, some of our largest customers rely on us to uncover and provide data within seconds, milliseconds in some cases, that are operational use cases that are operational nature. And the implementation being in C++ allows us to provide that kind of cutting edge performance. And finally, the storage architecture itself. Ours is a native data graph database, which means index-free adjacency design is built into how we store the data, so that all the connected data by design is close to each other. So there is no need to traverse and messages don't have to travel within the cluster as or at least limit as much as possible. So in total, the benefit is you're able to find hard to find patterns in the data easily. You're able to support operational use cases because of the performance. And then you have a one generic system that supports both transactions and analytics, which is our position, which is how we position our product. Now, coming to the second key feature area is the scale. Now you can do all of the querying, but can you handle scale as the data grows? When you go from a few gigabytes to a few terabytes into even a petabyte. Our architecture does that. We are based on massively parallel MPP architecture, massively parallel processing architecture. So everything is distributed. Now, as you grow, as your size, data sizes increase over time, you just add hardware and you're able to keep the same performance and ability to support larger data sets. And also the way we store data is in a very compressed format, so that the footprint is very small compared to the data that you bring in. That makes us efficient in terms of how we store as well as messaging. If you have to communicate across nodes, everything becomes easier. And from a benefits perspective, basically in this way, you integrate all your data. Your source data systems may bring in all sorts of data from databases, files, from input streams. We're able to integrate everything in one system. And we're able to partition the data so that the load is uniformly distributed across the cluster. And also we allow based on the MPP architecture principles, you can elastically scale resources based on what your needs are. So in a way, that's a benefit to only grow to the cluster to the scale that's needed. And the last aspect I want to check on a feature side is the analytics themselves. For us, one of the key things is the ability to do analytics within the database itself. And on the graph side, we really didn't have a language that was rich enough to deliver that. That's why we built our own language called GSQL. This is a high-level yet a Turing-complete language that provides you not only the basic querying functionality, but also ability to add procedures that user can express logic in a very rich way. And add to that, we have user extensible graph algorithm library, all of which runs in database. So you can pretty much run any advanced analytics algorithm, machine learning algorithms within database. That is if you choose to. But if you want to take it out to a downstream system, that option is also available. And the last thing I want to emphasize on the database, in database capabilities, is the ACID properties. All of our data is strongly consistent. So we ensure that all of the transaction management principles are followed, so that not only you do the analytics, but you can also be sure that the results are consistent. So you can support both OLTP as well as OLAP workloads. So basically, in a way, you have one system where you don't have to avoid, you can avoid transferring data out of the system for each workload, but rather unify your workloads on one system. Now let's look at the architecture itself. Like how do we accomplish this? If you look at our architecture, we acknowledge that TigerGraph is part of an ecosystem. So we have to pay. There are other systems that are there. So we allow easy way to cohabit with other systems, so that you can bring in data, historical data through our master data, or operational data through our suite of data loaders. And we also allow you to bring in data through RESTful APIs easily to ingest data into for any application that require. And then of course you have the GSQL language where users can insert data directly. All of these go through different avenues, but they eventually reach RESTPP server, which is our coordinating service that manages when the data comes in, parses and works with the engine to insert data into the engine. If you look at the core of the heart of the engine, there are three components that I want to spend more time on. One is the graph storage engine itself, which is where we store the graph storage data. We store the ID service. So our architecture relies on, for each record, there is an ID assigned, external as well as internal ID. So this ID service kind of translates when a data record comes in, how is it stored internally in the internal format. So the graph storage service basically addresses that. And the graph processing engine is the heart of the database engine, where we perform the parallel query processing, and we store the snapshots of data. Like if your query has updates, maintaining different versions of the copies of data, all of this is handled by GPE. And for data persistence, we use Apache Kafka. So any data that comes in either through SPP or directly through the data loaders is first stored on Apache Kafka for persistence before we push it to the engine. So in a way, no matter what your input mechanism is, either through REST API or Visual UI, which is, we have a Graph Studio UI that allows you to run queries and bring in data, as well as GSQL. All of them are unified through one interface, and the data is stored in the graph storage engine, and processing happens in a single unified way. And then we also know that as much as we do the in-database analytics, we also see that there's a lot of customers have investments in other applications like BI tools. They may have data warehouses where they want to take the data out of TigerGraph. So we make that easy even from that perspective in the architecture. We have a family of connectors that allow you to take the data easily out of the TigerGraph as well. That way, TigerGraph basically is a good citizen in terms of how it operates within the data management ecosystem. So one more aspect I wanted to touch base on is the deployment itself. Like distributed databases by design are obviously fundamental to handling large loads of data. And it is a core design principle for TigerGraph, and it's very beneficial, as you can see in the previous slide that I talked about. But there is always that concern that with distributed databases, there is an operational overhead, because we're dealing with a cluster of machines as opposed to a single machine. Now, from an architecture perspective for deployment, we have simplified that a lot. From a user perspective, it's very simple. When you need to set up a machine, you just have to figure out how much hardware you have, how many servers do you need to distribute data. Once you set that up, just tell TigerGraph system through the installation how many servers you have. TigerGraph seamlessly distributes the data. From a user perspective, we are not talking about user doesn't have to see machines as individual, but one single database. Even if you add more machines to it, it's still the single database that they program against. So they do not have to have any knowledge of the internals of how the data is stored, how is it distributed, and all that. So as your data grows from, say, single terabyte to multiple terabytes and so on, the user doesn't really have to know where is the data being loaded, how is being written. All of this is, these details are hidden and simplified in some way. And the second thing is the consistency itself. The writes that happen in our system are HA by design. So whenever a write comes to our system, it's returned to all the replicas, and the reads can be from any of the replicas. So as soon as the data is ingested or written, the user gets the acknowledgement, and then the data is ready for querying. And that way you have this really strong, consistent model, and user doesn't have to worry about, does the data is there in the system or not from a durability perspective. So just to recap, from a deployment perspective, what the advantages are, no matter how complicated your data needs are, how large and scale you are, the setup is still simple and simple to manage based on our utilities, from installation or upgrade, other scenarios. And from a scale out perspective, obviously, it's just a matter of adding more hardware as your data size increases. And the fact that we have massively parallel processing built into our query processing, it allows you to scale and run really large queries, any OLAP queries. And then the fact that we have strongly consistent asset property enforcement, which means you can run any OLTP queries at any time. And then the last but not least, the economics of it. The fact that we distribute the data, I mean, try to load balance everything, allows you to get most out of your investment from a economics perspective. Okay, so I want to switch gears now from system architecture overview to more each of the aspects of how we deal with the system. So in this case, there are different ways to bring in data into system, right? As in most cases, the data comes into TigerGraph from upstream application or a database, or even just a collection of files that have been exported from one other system. So TigerGraph basically provides various different ways to ingest data. And the reason for that is we wanted to provide flexibility so that the user are the best judge of what suits for them in each case. So let's quickly go over what the ingestion process looks like. As I mentioned, there's different ways to bring in the data. So the three key ways you bring in the data is you can bulk load the data through files, bunch of files that are there through one of our loaders, or you can bring in a Kafka stream. The formats that are supported for this is CSV or JSON. The second way you can bring in is through the REST services through a HTTP post request. Here the request has to be in JSON format. And the third is the GSQL insert command, which is basically an end user running a GSQL insert statement. So once the request comes in, we have a service called Dispatcher that takes in the data ingestion request and starts the following process. One, it'll query the IDS service, the GSC, to get the internal ID, because for each record that comes in, we have from the external to internal, there's a mapping. And after they get the internal ID, we convert the data into an internal format. And then the data is sent to one of the GPs to do the processing and store it inside the database. And then as each GP consumes those updates, and it's from periodically, it'll write it to disk so that memory and disk are in sync. And here I wanna quickly add one note about loading. Whenever we run a loading job or a post, the semantics we use are absurd semantics, which means if the vertex and edge doesn't exist, we create it on the fly. And if it exists already, we basically update it. Basically, it's an idempotent operation. Anytime any operation happens, it's if you repeat it, obviously there's not going to be a duplicate. And a quick note on what Dispatcher is. The Dispatcher is a internal module that is to schedule and dispatch tasks for a query. Dispatcher is not a separate process, but it runs inside REST API server and loader, it basically assigns a particular instance of GP to serve as a master. As in many MPP architecture, you have a master instance worker, and then you have worker nodes, so that the query runs in different servers. So let's quickly walk through one example. Here's the one scenario of data load. Data load, data can be brought in, as I said, as in CSV or JSON format. First, the data load request is passed to REST-PP, routed through the Nginx load balancer. From REST-PP, the data updates are returned to Kafka for initial persistence. This ensures that the durability of data is there before we write it to the TigerGraph system. Now, Kafka write-ahead log here is essential because it allows us to reread the data if there is any need. And the internal Kafka clusters that are used are organized based on the cluster layout. Like, for example, Kafka topics are that we set up are arranged based on the number of partitions in the cluster. So data belonging to a particular partition, which is categorized by each vertex type, is sent to the corresponding Kafka topic. And from that Kafka topic, GP ingests the data into memory. The updates are held in memory and is available querying immediately. An acknowledgement is sent to the users, basically indicating that the data is ready. And then we have a background process called rebuild that from time to time compacts all the updates in memory and writes to the disk so that the disk and memory are in sync. So this is kind of the high level overview of how an ingestion request would go through and go through the system into the disk. So one other thing I wanted to emphasize is when I say internal format and how we store data, I wanted to quickly define a few things as to what is stored exactly inside the database. TigerGraph is a native graph store. So when we write data to the disk, our goal is to make it easy for traversal and retrieval later. So here the principles again of index-free adjacency come into picture. So the three things we store for each record are listed here. First is the IDS, which is basically the bidirectional mapping between external and internal ID of each record in the database. The second is obviously the vertex data. As you store vertex partition data, all of the attributes for each vertex are stored alongside in the same location, so they're co-located. And the edge data is also stored, co-located, and edge data is basically partitioned by source and target internal ID keys. And then obviously all of the attributes of the edge are also stored together. So these three pieces of information are stored in segments inside each partition. And the principles there are, so the data is automatically partitioned to distribute across the cluster, right? So there's two concepts that I want to highlight here. One is the concept of partition, and the second one is segment. Partition is the unit of division of resources in the cluster. So the goal is to partition resources uniformly across the cluster. Basically, this allows for even distribution of the load and the resource usage later. So partition data is again is broken down into smaller units called segments, and segments are picked in such a way that each segment belonging to the same vertex type is stored together. And this basically ensures your data locality so that you minimize the need for movement of data across cluster as much as possible. As you can see in this example here, each segment, all of the data belonging to each vertex and edge that is by ID is co-located on each segment and in each partition together. And location of any of the vertex can be easily calculated based on the internal ID, and vice versa translation can happen as needed during the query processing process. So that's the ingestion process. Now moving on to the query processing, which is a little bit more complicated because as we support multiple workloads, there are different ways to handle query processing. I'll go over a few details in this section. So first, let's go over what the workflow looks like for a query processing. So user runs a GSQL or a Graph Studio query or a RESTful API calls to submit using HTTP request. Once the user submits, REST server parses the request based on the graph schema and forwards it to the dispatcher. And the dispatcher will query the ID service to convert the request from the internal format to the external, and also assign a particular GP as the master for that query. And from that point onwards, GP performs the computation based on the user logic of what the query is, and then returns back to the dispatcher the run result. And this is again sent back to the REST server. From REST server, obviously the result is sent back as a HTTP request in JSON format back to the user. Fairly high level overview of what the workflow would look like. Now, one thing I wanna, before I go further into the details about the query processing, I wanted to spend a few minutes on how the memory is used itself, because memory is so vital to how a TigerGraph performs. I wanted to spend a couple of minutes on that. The reason why it's also important is because the way you optimize the memory usage helps the query performance. More memory, if it's available to system, there's more opportunity to speed up the performance. So here, the way memory is divided is in two broad categories in TigerGraph. One is the static reserved memory that is always used by system. And the second one is more query level usage that can change depending on the load. So any reductions we do with the system level static can mean more memory is available for query processing. In terms of the first category, the static memory, let's start on the right side. Here, there are two key principal users of that memory. One is the GP, which stores all of the partition data, all of the graph data, including vertex, edge, attribute. All of this is preloaded by default in memory. And the second chunk of memory that's utilized, reserved, is by GSC for IDS, where we preload all of the IDS data in memory. So this is something that's a constant, and it's configurable, where users can set limits of how much memory they want to retain in for this the data, and how much they want to put it in disk. But the other aspect of memory that's used is dynamic, which is basically depending on what query is running. Here, as you can see, bulk of the query used by memory can come from accumulators, concept I'll explain later. And they also, some of the memory is used by shuffles. It's also memory used by, if the query has upserts, then we need to maintain copies of the data, which means additional memory is required from a GP perspective. So all in all, you have two sets of categories of memory. One is the static one that you can configure from an operational perspective. The second aspect, the query dynamic memory, that is something that can be optimized based on your best practices. And that's where a lot of the training helps to get more out of TigerGraph system in terms of memory usage. Okay, so let's look at a quick query processing workflow from a query processing. So here, if you look at a typical processing, we'll start at the top. Request comes in, the incoming requests have details such as query name, parameter, and schema information such as vertex, edge type. It goes through Nginx again to SPP. RESTPP parses the request, and the first action is RESTPP will send the request to GSC to get the to translate the external ID into the internal ID. And at the same time, RESTPP will send through the dispatcher to the master GP the query name and other parameters. And after GSC returns the internal ID, the processing moves to GP. And at this point onwards, GP will basically do the query processing based on the user logic. And all of the computations are performed depending on if it's a simple query versus a distributed query. After all the processing is completed, GP responds back to GSC to get the external ID of the vertex that's in question, and sends the JSON response back to RESTPP, basically returning the result of the query. And RESTPP then combines the the responses from all and then sends it back to Nginx, and the query result is finally returned back to the user. So it's kind of the high level overview of how query workflow occurs. One thing I want to spend a minute on is, I know there are multiple ways to query data from TigerGraph, but GSQL is the most comprehensive one. And there's a number of reasons for that. One, because GSQL is based on schema based query language. It allows you to have integrity checking. It allows you to basically make your app development data independent. You don't have to have knowledge of how the data is very stored. So it kind of helps from that perspective. And also we have built in some high performance features like accumulators that allow you to work independently in parallel towards improving the performance. And also GSQL is like SQL, the familiarity of all the SQL users, that input is taken into GSQL. So someone coming from SQL can easily understand GSQL syntax and can get started easily. And in addition to that, we also made it easier to implement algorithms. A lot of the control flow functionality, like for example, for, while, the loop, basically seen in programming languages are available through GSQL. And then you can parameterize queries so that you can reuse the code. So all of this makes it easy for complex query to be reused as much as possible. And finally, GSQL also supports transactional graph updates, which basically makes it suitable for both analytical as well as transactional use cases. So you can use it both. So just a quick overview on that. And now I want to spend a few minutes on what are the different querying patterns themselves, right? If you think about MPP system, it's not a one single system. It depends on the type of workload you run. The system is able to adjust and provide a way to leverage resources in the most optimal way. So we have in our system two modes in which you run queries. One is called a single server mode, and the second is distributed mode. A single server mode, as the name suggests, basically concentrates all of the query processing on a single server. Like for example, if you have a query that's a simple query, then the cluster elects one server to be the master, and all of the computations happen in that master. And if the data is not in that particular server, we actually copy all of the data and bring the data to that particular node. And then all of the processing happens on that single node. And this is useful for simple queries where you are only dealing with a subset of vertices. Now, the second one, other mode is the distributed mode. Now, as the name suggests, this is again contrasting with the single server mode. Here, the processing is totally distributed. There is no single, the server still picks a master as for a query where as the master, and then the worker nodes are all working in parallel to do the computations. So here, again, the power of accumulators comes into picture. Any query that's running in parallel, all of the computation that have to happen in parallel happen, and the results are aggregated at the very end, and then the query, basically the power of parallelism comes into picture here. So if your query is something that uses all of the vertices or most of the vertices of the graph, then this is a good way, because then you're bringing all the power of entire cluster for query processing. So again, to do a quick recap of where to see which one is useful. So if you are starting with a small number of vertices, then single server mode is best. Example, point queries. We call point query one that is where the predicates are very simple, or you can dealing with a very small subset of vertex data, then basically like transactional queries, OLTP queries. These are the ones that are best fit for single server node. Now, if you have complicated algorithms, graph algorithms, or OLAP style queries that require large number of vertices, edges to be traversed, then obviously you should use distributed mode. And obviously here, like example, PageRank, centrality lowing, these are the sort of algorithm that typically require you to deal with entire data set. So those would be the ones would be a good candidate for distributed mode. Now, I want to spend a couple of minutes on accumulators because I did make a mention about the fact that they are unique in the industry in graph databases. So I want to spend a couple of minutes on that. So accumulators are a new innovation from graph databases. They kind of allow us to enable parallel processing of data as much as possible. They, as the name suggests, accumulators basically accumulate information about the graph during traversal, and they enable multi-thread processing as much as possible to speed up your querying. So accumulators work in two phases. In phase one, basically you receive messages, and during the traversal, accumulators hold all of the message data in a bucket that belongs to the particular accumulator. In phase two, the accumulator will aggregate based on the type of aggregate function that's defined and compute the value and provide it for the query. So again, in terms of accumulator, there are two types. There is one local accumulator, and then there is the global accumulator. Local accumulators store data about each vertex and can only be accessed by the traversal instance. They're basically runtime attributes for each attribute. If you run into the same vertex again, then obviously you can use this in the same query block. You'll be able to use that information. Contrast that with the global accumulators that store information about the entire graph, and they can be accessed by any node. And if you look at the accumulators, like I said, there are different aggregate functions that can be performed using accumulators. We have the ones we have are sum accum, which keeps a running total of the integer totals. It's basically a cumulative concatenation of all the values that are there. And the next we have min and max, which obviously store the least or the greatest value of a series of values that are encountered in a traversal. And then of course we also have the average, which computes the average and stores the mean value for a series of numeric values that are seen in the graph traversal. So these are very useful for OLAP queries, where if you want to push down the computation to the worker level as much as possible, rather than have it bring in data into the master node, basically implementing it in the true distributed computing model. So this is a quick overview of the ingest and the query processing aspect. So now we want to shift gear to non-functional features. Victor will go over that. Victor, are you ready?
Thank you, Reyes. Yeah, great job. So I'm going to cover 3 areas: high availability, access control and security, and transaction management. So if we go to the first slide on high availability. So as Reyes showed you earlier, you can have a distributed system and you can have replicas of that. So I'm going to introduce a couple terms. P is the partitioning factor. So if my database is spreading the data across 5 servers, that's the partitioning factor is 5. And then if I have 2 replicas of that entire database, then my replication factor is 2. So I have a total of 10 servers. And this is a pretty, traditional architecture that gives you both. Now, depending on what exactly a replica can do, whether it's an active-active replica, whether it's a read-write replica or not, depends on what benefits you get. Because our replicas are active-active, they are read-write, meaning they're always in sync. Every replica has the same data when a transaction finishes. Then you get both increased throughput and you have the benefit of continuous operation if you've engineered it correctly. So again, that's some basics. Let's go on to the next slide to look at how you get that throughput. So now I've numbered the systems. So they're 1 through 5 going across the partition, and A, B to refer to the replicas. So, and we say each server, this is a configuration factor in the TigerGraph software. You can say each server has a certain number of available workers for serving requests, such as a GSQL query, a REST post request, etc. the default's to 8, but you can set it higher. And you might want to be thinking about how many CPU cores you have, because there's a correlation. It doesn't have to be the same number, but it's influenced by that, what sort of performance you get. So that means the total number of workers you have available is T times P times R. So in this example I gave, if we have 8 workers per machine, then you have 80 workers. A point mode query, when Reis earlier was talking about the 2 processing modes for queries, a point mode query uses 1 worker. The worker has to be in charge. Other servers may assist, but we're referring to who's kind of doing coordination work. A distributed mode query, on the other hand, uses a worker on every server across one replica. So it's using P workers. So that means you have a lot higher level of concurrency if you're doing point mode. You can still have very good concurrency in distributed mode, but it's going to be somewhat lower. So that's basically the scheme for, we didn't go totally, I'll say a little bit more when we get to transaction management about how the concurrency happens, but this is explaining the level of concurrency that is possible. In the next slide, I go into what happens when one of those nodes goes down. So next slide, please.
Yeah. Oh, okay. Yeah.
So we're designed to provide continuous operation. So if any single server goes down, either because you intentionally take it down for service, or there's a failure, so it's unexpected, the other machines will be trying to contact it. And if it fails to respond after a certain number of tries, then the request will automatically divert to another replica. For example, if 3B is unavailable, then the request will shift to 3A. So it may have, if that failure happens in the middle of a transaction, probably that transaction is going to be aborted. But if a new transaction starts and it already sees that 3B is not available, it'll just work around it and go to 3A. And so other subsequent transactions will run fine. So there is continuous operation. There'll be obviously reduced throughput, but you won't have to go down while you're trying to make repairs or do your service work. There will be a short pause while you bring it back online, and we're working to even cut down on that time when you bring it back online. So that is our basic story on HA. I'm sure there'll be some questions later, but we're going to move on to access control. And I'm going to cover a couple things here. First of all, we feature role-based access control, an industry standard model for how you should, enterprises would like to see roles and privileges and users managed. So we very much follow the language semantics and language syntax and semantics of SQL. So you can grant or revoke a role or privilege on a graph instead of a table, and then to one or more users. And you can also map those roles to external LDAP roles and groups. So you can combine the roles you have with TigerGraph and sync them with the roles on other parts of your larger infrastructure. So I'm going to go now into a little bit more depth. You can also manage the roles in the latest version of Graph Studio, which includes a admin portal upgrade. So you can see the different users and different privileges are listed there. And so you can, rather than writing lines of code, you can manage them, and an admin user can manage them through a UI. The next thing I want to talk about is the graph component. So I said a privilege is, there's a role or privilege on a graph for some number of users. And a unique feature and benefit of TigerGraph systems is the multigraph feature. It's the way that you can define subsets, subgraphs, or views within your larger graph that not only can be used for pure isolation, such as multi-tenancy. You can have completely separate data domains, but you can also intentionally choose to overlap them. And so then you're enabling sharing. And as the picture shows, you can have regions like the product group. They have some data which is only theirs. They have some data which they share with IT. They have some data which they share with the customer department. And they have some data which all the teams can see. And you can very easily define very sophisticated combinations of both private and shared data. And because it's actually shared, not copied, you're guaranteed consistency. It's less expensive because there's less hardware. There's only one copy of the data. So it's consistent. So it's cleaner, faster, cheaper, and safer. And as I said, each group also will have its own administrator. So that's their worldview. They don't see the other groups at all unless the super user enables them to see the other groups. So within each group, it's like they have their own graph. They manage their own affairs. And it's a great two-tier model of global and local privileges. And you can do really interesting combinations of how you define those graphs to achieve really interesting results. And I'm going to have to move on so we can try to wrap up on time. We have a number of built-in roles, and we currently have user-defined roles in development. So for the built-in roles, it really follows a hierarchy as well as two different branches. There is, those who are designing the graphs and designing the queries, and those who are managing users. So, at the lowest level, this is, I've written down the lowest level query reader, and the top level is obviously super user, but I'm not going to spend the time to go through everything here, but you can see you've got, even with the built-in roles, you have pretty fine-grained access control, and we're going to be giving you even finer-grained control in the near future. So I'm going to move on to data encryption. So we're kind of generally talking about security. So obviously this is very important to a lot of users, and there are two basic things that enterprises need. They may want the data to be encrypted when it's stored at rest, as we say, and also when it's being sent from one place to another, encrypted in transit. So for at rest, we give you a choice of several different encryption levels. It could be file level, volume, partition, or disk. And we give you a choice of techniques you can use. If you're doing kernel level encryption, where you need super user privilege on the machine, one of the most popular approaches is to use the built-in Linux utilities, dmcrypt and encrypt setup. If you don't have that option or don't want to do it at the super user kernel level, you can do it at the user level using Fuse. TigerGraph Cloud, by the way, automatically is encrypted, so it's nothing you have to do there. For encrypting data in transit, you can set up SSL TLS so that it's using the secure HTTP protocol. It's a fairly standard process of getting a certificate and just a few configuration commands and you're set. Because as Reis mentioned, we use a lot of REST requests, which make use of HTTP protocol. So even within our own system internally, we're using HTTP as well as for possible external communication. So this is something that we've thought about early on, and so it's fairly straightforward. And also, it's automatically encrypted in TigerGraph Cloud, so nothing for you to do there. And that's the security topic, and I'm going to move on to the last topic, transaction management. So we are a distributed database, and we are a full ACID database using the sequential consistency model. There are a lot of different consistency models these days, and so sometimes you need the fine print, and so we're going to have just enough time here to give you the overview of what model we follow. So first of all, what is a transaction in TigerGraph? So when we say a query, and this is where it's a little different, it's because of the programmability of GSQL language. Our queries are procedures with a name and with a parameter list, input parameter list, and within it, it can have multiple statements such as select, insert, update. It can also have flow control like for loops, while loops, if, else, case, when. But we consider one query, which is a procedure, to be a transaction. So clearly it can have both read and write operations in it. It could be read only, it could be write only, it could have both. Also, if a user is doing things just as a REST request, one REST request is a transaction. So that's the model of what is a transaction. And then we're going to go into the ACID compliance level. So we got ACID, ACID, atomicity. I already explained what is a transaction. And so obviously they are all or nothing. Either it completes completely, successfully, or not at all. Like I mentioned, if there is a failure of one machine in the middle of a transaction, that one will probably fail. And so none of the changes regarding that transaction will take place. Consistency model. The term ACID was defined before distributed systems were popular. When they defined ACID, they were really talking just about single servers. So the original meaning of consistency has to do with just, is your transaction obeying some basic data validation rules, such as referential integrity? So obviously we obey those. What's really interesting to people these days is what sort of distributed system consistency do you have? And so as we said, we have sequential consistency, which means each replica of the data performs the same operations in the same order or same sequence. Moving on to isolation level, we're very strong isolation. We guarantee repeatable reads because each transaction sees the same data within that transaction. If you read something at the beginning, read something in the middle, read something at the end, if you haven't made any updates, you're going to be reading the same data. No change there. And no dirty or phantom reads. If one transaction makes some updates, other transactions are not going to see those updates until they're officially committed. So got strong isolation there. And durability, and I think this even relates a little bit to maybe peripherally to a question that came in about a different database. We use write-ahead logging so that, as Reyes mentioned, the updates are written to disk at the beginning, and they stay there in a log so that you've got that durability. But that log is not what you consider, the database proper. The database proper is conceptually, that's the graph. That's so periodically we consume the recent logs to update the graph. But because you got those logs, there's a guarantee that you can take the current graph and the as yet unprocessed logs to reconstruct what the graph should be. And in fact, that even is used in concurrency because other transactions are taking place before the graph has been fully updated. So they're using those logs to understand what's the quote current state of the graph. And that basically, that's all the time we have to do for presentation. We have a lot of questions. We have a lot more information you can find on the web. Please contact us if you have more questions, but let's get right to some of these questions. I'm just gonna go top from bottom. I'm gonna read them out loud, I guess, and sort of between Reyes and I, we'll decide who actually answers it. One, does the storage engine manage partitioning under the hood, especially as you scale out horizontally? Reyes?
Sorry, I'm on mute. Oh, I'm not. Yeah, so from a scaling perspective, it is like I said, the principles of MPP take over here. Basically, the auto partitioning. Basically, we have a round robin algorithm that distributes data evenly. So from user perspective, it is totally transparent to them. We basically handle it in as part of our design.
Okay, number 2, how do you hide communication latency when fetching data from a remote processor? How do you load balance work across processors? So I'll take that one. What we have is we have minimal communication latency because we are being very careful about how much and what we need to communicate across the graph. Now, we don't make wild claims about doing an optimal partitioning of the graph because that's an NP-hard problem. It's not doable. What we do, as Ray showed, we do as much locally as possible and then only transmit the data that needs to be known by the other systems. So it's not a question of hiding the latency. It's about minimizing what needs to be done. And it's about working, while you're working within the machine, you're going as quickly as possible. How do we do load balancing? We have a number of schemes. You know, we start off with round robin. I showed earlier how many different workers are available. So, you know, the masters who are in charge of a query are looking at to see who's available. And it's also up to the workers to respond about whether they're available, how much load they currently have.
Yeah. So dispatcher has the cluster view. So dispatcher kind of knows what is the level of activity on each node. So dispatcher decides where to assign the queries.
Third, can you share numbers around high transactions supported for ACID? Basically, how many transactions can we handle simultaneously? You know, there's a lot of system dependent issues there. So we can get back to you with some numbers. Fourth, your data sources. How would I connect to solutions like SharePoint or OpenText? So, you know, the general mode is our basic format is we read from files or from Kafka or from certain data stores. We also have a JDBC connector. We'll soon have an ODBC connector. So if you have one of those standard formats, we can work. So, you know, the bottom line is also, well, if you can put your data into what looks like a file, we can read from the file. But if you're looking for a more app-to-app connection, we have JDBC and we'll soon have ODBC. And our community is building lots and lots of more connectors. Let's see how much more time we have. For HA on AWS, how do you deal with or support multiple regions in terms of ACID, writing to all nodes, and the cross-region latency? And that might be the last question we have time for, but Rais, you want to take that one about cross-region setup?
Yeah, cross-region perspective, single cluster, you can set up across regions, but you have to be cognizant about the network latency. We rely on AWS cross-region replication mechanism to do that. Now, if you want to have clusters set up, so disparate clusters across regions, that's a feature in development right now, because you could set it up yours we have a solution in that customers can implement. But to do it natively, both for data operations as well as metadata operations, that is a feature in development and will be available soon by the end of the year.
I'm going to hand out two more very quickly. Replicating data eats up a lot of memory. Well, if you look at our replication model, it's based on setting up another copy of the servers, and that's just the standard model. We have data compression, so if you have X number of bytes of data externally, when it's loaded onto TigerGraph, chances are it is only half the size. So it may not be as much memory as you think. In other systems, other systems require replication just to operate. We don't require that. For us, replication is just because either you want higher throughput or you want higher protection against, possible, hardware failures or whatnot. Other systems like Cassandra, you have to replicate, or pretty much it's very strongly recommended. For us, it's merely your decision. And the last question, how do we handle errors during bulk loading? We do line-by-line checking. The log, we will tend to, if there's some reason why a single line cannot be processed, the error type will go into the log and it will move on. So it's going to try to just process every single line or every single JSON object individually. It will log a bunch of different errors it encountered, and you can look at the log when you've finished. And I think that's all the time that we have. We want to thank everybody for joining us today. You have been part of one of our biggest webinars ever. Certainly the most questions I can ever recall receiving, and we will answer the questions individually, getting back to you if we weren't able to answer it online today. I'm not sure if Emily's on there, but I'll just.
Yeah, I think I want to second Victor for all the interest that you've shown. And if you're new to TigerGraph, you can try very easily TigerGraph Cloud, easy to set up and test drive yourself. You can also download Developers Edition to get more on your own environment. And then the resources are all there. There's a growing community, very vibrant, managed by our developer evangelist who can answer questions. And also, there's also TigerGraph certification program if you really want to get certified in TigerGraph internals.
Thank you again.
Yep.
Thank you.
We
Thank
look
you.
forward to hearing from you again.
Thank you. Bye-bye.